Good morning. This is your Stat Sensei, Mr. Spensei, and in this video, we're going to be comparing central limit theorem to just plain old normal distribution problems. So, our first problem: a brake manufacturer designed a new brake pad for long haul trucks. Repeated tests were conducted on long haul trucks transporting a load of 75,000 pounds at 70 miles an hour. The braking test showed that the new brake pad allowed the trucks to stop completely in an average distance of 515. So they're telling me the mean is 515 with a standard deviation of 62.5 feet. The braking distances are approximately normally distributed. Okay, so that means I don't need to worry about sample size. What is the likelihood that a single long haul truck with a new brake pad has a braking distance between 545 and 605? First off, they're telling me this is a single truck. Single truck tells me I'm probably going to be looking for a norm CDF. Let's go ahead and draw our picture here. They said that the mean was 515, but we have a stopping distance of 545 to 605. And we're looking for this distance right there. All right. So my probability statement is going to be the probability that 545 is less than X is less than 605. So I'm going to have a norm CDF, and it's going to go lower bound is 545. That's the lowest part of my shading, all the way up to a 605 with a mean of 515 and a standard deviation of 62.5. And as you'll remember, that's our LUMO, L, a lower, upper, mean, and yeah, that's not a zero, but looks kind of like one. So here we go. Second vars, normal, CDF. Oops. Second vars, normal, CDF. I'm going to clear that. There we go. And we have a 545, an upper bound of 605, a mean of 515, and a standard deviation of 62.5. So that gives me about 24%. So equals 0.2406. Box that answer, about 24%. Next problem. What is the probability that a randomly selected a sample of 15? Oh, we have a sample size of 15. So that changes things a bit. Have a mean stopping. So we're looking for an X bar of at least 545. So we're looking for the probability that X bar is greater than 545. So if I'm drawing my picture of this, we have a mean of 515. We have a X bar of 545, which is above the mean, and we're looking for this value. So in this case, we're going to be working with a z-test. So we need to write down our formula because we're going to have to plug into this. So we're going to have z equals x bar minus mu standard deviation divided by the square root of n. So we were looking for the probability that z is greater than x bar of 545 minus a mean of 515. Standard deviation in this case, well, they told us earlier that our standard deviation is 62.5, but we're going to have to do the standard deviation of x bar, which means we have to divide it by the square root of our sample size of 15. So I'm going to go run a stat test z-test and see what we get out of this. Stat test, because anytime we're working with an average or the mean, that's where we want to go. Stat test z-test. And 515 was the mean. We have a standard deviation of 62.5. That's the population. We have a sample mean of 545, and we have a sample size of 15. And we want to know the probability is greater than. Make sure we have that highlighted right. And we have the probability of z is greater than 1.859. Probability that z is greater than 1.859. and that equaled 0.03, so less than 3%, equals 0.0315. We can box that answer, and that's our answer for that problem. The distribution of SAT scores is approximately normal. Okay, so they told us normal with a mean of 1051. So mean is 1051 and a standard deviation of 211. All right. Um, what is the likelihood that a randomly selected student has taken the SAT has scored between 1070 and 1240? That tells me my sample size is 1. If we're working with a sample size of 1, we want to do a normal CDF. All right, so that lets me know I'm doing a normal CDF. But what am I looking for? I'm looking for the probability of 1070 is less than X is less than 1240. And the way that looks on the graph is something like this. We have a mean of 1051. We have a 1070 above it. And we have a 1240 here. So I'm looking for that area right there. Both of them happen to be above the mean because 1240, 1070 is above the mean and 1240 is above the mean. Normal CDF, lower bound 1070, upper bound 1240. Oops. Mean of 1051 and the standard deviation of 211. And that's my lower, upper, mean, standard deviation. I guess I could rewrite that a little bit better. So how about I do that? Norm CDF 1070, 1240, 1051, and 211. That wasn't much better, but hopefully that helped you see a little better. So let's go to the calculator. Stat test, second vars, norm CDF, lower bound 1070, upper bound 1240, mean of 1051, and standard deviation of 211. And we get about 27%, so 0.2789. All right, the next one. What's the probability that the SAT score that the average, so we're looking for an X bar of a random sample of 25, so N is 25, that's going to be important, is less than 1,000. Well, let's draw our picture. Well, our picture is centered at 1051, and we want to know the likelihood that it's less than 1,000. So that goes to negative infinity. So probability that X bar, because it's the average, is less than 1,000. And we have a sample size of 25. So we need to use our Z formula. So Z equals X bar minus mu standard deviation divided by the square root of N. So we want the probability that Z is less than 1,000 minus 1,051. Population standard deviation happens to be 211 divided by the square root of 25. Second, so now we have a Z, so we're going to use the Z test. So stat test, Z test. The mean is 1,051. The X bar is 211. The X bar, the population standard deviation is 211. The X bar is 1,000, and our sample size is 25. And we end up getting a negative 1.208. So the probability equals the probability that Z is less than negative 1.2085, and that equals 0.1134. Let's box that answer. Okay. All right, next problem. The manager of a cultured pearl farm has received a special order for 2 pearls between 9.5 millimeters and 10.5 millimeters in diameter. From past experience, the manager knows that the pearls found in his oyster bed have diameters that are normally distributed with a mean of 8.5. All right, so we have a mean of 8.5. We'll note that down, and a standard deviation of 3. What's the probability a single pearl is too small to satisfy the size requirement? So let's draw a picture of this. First off, we're working with a single pearl, so that tells me I'm probably that I'm going to be working with a norm CDF. What's our picture? Well, he says normally distributed with a mean of 8.5, and the pearl has to be at least 9.5 millimeters. So we want to know the probability that it's less than 9.5. Please remember, normal goes to negative infinity. So we want to know the probability is less than 9.5. So our probability statement is the probability that X, our single pearl, is less than 9.5. So norm CDF, lower bound, negative infinity, upper bound can't be 9.5, mean is 8.5, and our standard deviation is 3. So there's our LUMO, lower, upper, mean, standard deviation. Second vars, normal CDF, lower bound -9 raised to the 99th, upper bound 9.5, mean of 8.5, standard deviation of 3. And we end up with about a 63% chance that it's going to be too small. So equals 0.6305. Next question. What's the probability that the average, they said average, so that lets me know I'm working with an X bar of 5 pearls. So our sample size is 5, is greater than 9. All right. And once again, we have a mean of 8.5 and a standard deviation of 3. Same information we had before. We go ahead and draw our picture. And we know the mean is 8.5. But we're wondering what's the probability we get a 9 or greater for our X bar. And remember, this goes to positive infinity. But since we're working with an X bar and not a single pearl, we're going to need to use Z equals X bar minus mu standard deviation divided by the square root of n. So I want the probability that Z is greater than 9. That's the size we're interested in. 8.5 is the mean. Standard deviation of the population is 3. And we want to know the likelihood that we'd have get an average of that, of those 5. So let's plug that in. Stat test, Z test. Press enter. Mean 8.5. Standard deviation 3. X bar 9. Sample size 5. And we wanted greater than. So make sure we have greater than highlighted. And there's about a 37, we get a 0.3 z-score. So the probability that z is greater than 0.3726 equals 0.3546. 0.3546, and that's the answer we're looking for. There's about a 35% chance that the average pearl size, if you had a group of 5, would be greater than 9 millimeters from this. All right. What is the likelihood that A random? A is 1. The fact that we're working with 1 tells me I'm looking for a normal CDF. So let's draw our picture. I'm trying to draw it a little larger this time. We have a mean of 8.5, but we want a pearl. What size pearls do we want? We either want a 9.5 to 10.5 size pearl. So there's 9.5 here. Here's 10.5 right here. And I want to know the probability that that single pearl lies within that interval. So my probability statement is the probability that 9.5 is less than X is less than 8.5. And remember, our mean is 8.5 and our standard deviation is 3. So this is going to be a normal CDF. Our lower bound, our lower part of our shading is 9.5. Our upper part of our shading is 10.5. We have a mean of 8.5 and a standard deviation of 3. So this is my LUMO. Lower, upper, mean, standard deviation. Second vars, normal CDF, lower 9.5, upper 10.5, mean 8.5, standard deviation of 3, and we get a probability of 0.1169 equals 0.1169. Box that answer. We're good with that one. All right, next one. Beef ranchers. Beef ranchers sell cattle at auction. The more cattle weigh, the more the rancher makes. While there are numerous factors that determine the weight of cattle, the rancher can impact the size by waiting until the calves are older and by changing the quantity and quality and type of food that the calves receive. One particular rancher has a herd of cattle in which the weights of his calves are normally distributed with a mean of 560. So I'm going to note that down, mean of 560, and a standard deviation of 123. What is the likelihood that a randomly selected, I see the word random, that means 1. Anytime it's 1 is a normal CDF, weighs between 480 and 525. So let's go ahead and draw this picture. Well, the mean was 560, and apparently we're going to be below it at 525 and our lower part at 480. And we're looking for that area. Well, since this is a single value, this is going to be a norm CDF. So I'm going to go ahead and make a note, norm CDF. And I want the probability that 480 is less than X is less than 525. So lower bound 480, upper bound 525, mean 560, standard deviation is 3. Lower, upper, mean, standard deviation. Second vars, normal CDF, lower 480, upper 525, mean 560, standard deviation, not 3, 123. 1, 2, 3. And we end up with about a 13% chance that a cow would be in that range, is 0.1302. All right. 18. Oh, we have a sample size. So N is 18. We still have the mean of 560. We still have the standard deviation of 123. Are ready for auction. And weighed, what is the likelihood that their mean weight, we're looking for an X bar, so this tells me it's a Z test, is more than 600 pounds. All right. So if I'm drawing my picture, we're centered at 560, And we want to know the likelihood that we are at 600 or more. So z equals x bar minus mu standard deviation divided by square root of n. Probability that z is greater than 600 minus 560 over 123, sample size 18. So stat test z-test, stat test z-test. The mean of the population is 560. The standard deviation of the sample of the population is 123. The x bar, the mean of the sample, 600. The sample size was 18. And we want to know the likelihood that's greater. And we get a probability of 1.379. Probability that z is greater than, that's our z-score, not our probability. Sorry about that. 1.3797 equals the probability being a 0.0838. All right. And I sure hope that helped. And I hope I didn't confuse anybody there please remember the 1.379 is my z-score and the 0.0838 is my probability. All right. I appreciate you watching and I sure hope to see you on the next one. Thank you.